minute. Good morning.
Hello.
Hi, Nicola. We will start in a minute. Maybe I can stop sharing the screen so that you can
Sure.
you can upload you can share yours.
Okay, you see it?
Yes. Okay, we can start. So it's a great pleasure today for me to introduce our two speakers for the third Netpore webinars. We have two professors, research scientists from the academic world this time, working, of course, material and semiconductor or oxides. It will be very rich with a lot of examples of different materials, and mainly this time applied to health and biomedical applications or biosensing. So the first talk will be given by Nikola Knežević, who is a senior research scientist from the Biosense Institute in Serbia. Nikola, if you're ready.
Thank you very much, Frederic, and all who organized this event, this opportunity actually to show our research. So yes, I will talk about mesopore nanoparticles and organosilica nanoparticles and bioactive nanosystems with these types of nanoparticles. So I will mesopore nanoparticles. I included this old photo actually from the first paper that involved these materials in Nature 92, that they are typically synthesized by a surfactant templated method using CTAB and other surfactants possible. So basically use this as a template and then make a mesopore structure and make silica and organosilica around it. And as you can see below on SEM and TM images, they are like, can be spherical or they can be different shapes also, can be fine-tuned. Also, you can see that they are porous, and this porosity is very well structured. So it's like a honeycomb structure. You can see the pores are 2 to 3 nanometers usually. And if we include the magnetic nanoparticles within the synthesis, we get core shell structure. So you can see spions, superparamagnetic iron oxide nanoparticles within these structures. And then we have a magnetic characteristic to this material. And the characteristics of this material are very well suited for different applications. So I will talk more about health applications, but you can use this high surface area for absorption of molecules, for organic functionalization, and for selective actual functionalization outside versus inside surface, etc. You can have different compositions. I will not talk about silicon nanoparticles, and I actually worked with some with Frederic before in Montpellier, but I will talk more about, you can see silica, MSN, and PMOs, which have this bridging organic moieties within the silica. And there are also other hybrid materials now with having PMOs mixed with MSNs and different stuff. But we usually work with pure PMOs and pure MSNs. And diameter of these particles can be fine-tuned, and pores can be fine-tuned, and they have high thermal stability and chemical inertness, which also can be fine-tuned with some other chemicals. There are different research possibilities once you have this material, and that can be easily functionalized with different organosilane, and then you can have different functional groups next to each other. So one, for example, for cancer targeting, the other one for imaging, and you can have, as I said, core structure, core magnetic nanoparticle or quantum dot nanoparticle, which I will also talk later, which can have more active role in the targeting and actually treatment of cancer. We can load different stuff, different molecules inside, and then trap the molecules with different also macromolecules and or other nanoparticles, more nanoparticles, which can block these pores, and then induce this release of therapeutic molecules with different stimuli. For example, target treatment of cancer. Upon weekly acetic acid, for example, these molecules can be released, or genes, or upon to trigger some triggers in cancer and tissues. This is an early example that we made actually. So with doxorubicin, just simply adsorbed on the surface, and then we have masked ammonium ions, amino groups there on the surface of MSN. And then we, upon exposure to UV light, this, you see, carbamate linkage is cleaved, and then releases these amine moieties, which are positively charged, and because doxorubicin is positively charged at the pH, physiological pH, it releases from the surface. So then upon more exposure, we get more released doxorubicin. You can see here, we monitor, we saw that we have this nitrovolatile group coming out. This is after centrifuging and in measuring supernatant, and you can see the changes, zeta potential, and all other characteristics that I will not talk about. But you can see also even before exposure to infrared, UV light, we saw high release. You can see below high release of doxorubicin at lower pH than at pH 7.4. This is actually innate ability of silica to release, to be protonated. So the surface of the silica at pH 7.4 is more deprotonated. So you can see silanols are deprotonated and doxorubicin is protonated, so it's attracted to each other, but then at 6.4, more protonation of the surface occurs, and then doxorubicin comes out. So that's in addition to releasing amine groups which are positively charged on the surface and then inducing the repulsion. But the other possibilities, as I said, include entrapping dyes, as you can see in upper panel, or drugs. This is amsacrin drug below. And then in this case, we entrap them with ruthenium complex. And this is enough to stop the release from the pores. So ruthenium complex is covalently linked to this surface inside the pores. And then, so this ruthenium sulfur bond, coordination bond, is being cleaved upon exposure to blue light, visible light. So we just use LED light, regular LED light. And then you can see here measurement of kinetics. So after 24 hours or so, there was no release of either ruthenium dye, because it's, you can see these two peaks actually about 200 something and 450 coming from ruthenium. And then also we measured separately the dye, because the dye gives this about 580 nanometers absorbance. So we can measure the kinetics after exposure to blue light, and both species have the same kinetics actually in this case. And we also, as you can see here, pores are being blocked after adding ruthenium complex, etc. And then also we measured the release of amsacrin. Also, this one had slower kinetics in case, because the amsacrin is shielding a bit, because it absorbs actually this irradiation with blue light. But we also tested if these dyes and drugs can be released actually even upon substitution, perhaps with additional some ligands, even with cyanide or histidine imidazole. This was not very effective release of the drugs, of the dye actually in this case, but only with visible light was cleavable. So we tested on cells, we showed that there was some effect in our conditions that we used on cancer cells. So we used other also in this case, capping molecules, this was hydroxylated fullerene, which actually just hindered a bit this release of this vinblastine, which is also anti-cancer drug, because it makes hydrogen bonding, of course, with the surface. And then you can see here, actually, even before, even with addition of fullerene, but without vinblastine, we did not see too much change on the surface, but only after adding vinblastine and fullerene, we saw some very agglomeration of fullerenes on the outside surface, etc. But actually, we modified also the surface with folic acid and targeting folate receptors, which are expressed in some cancers. And then we tested in cancer cell lines like HeLa, which have these folate receptors are expressed, and we showed that it has higher toxicity of these type of cells than other cancer cells, which like MCF7, which do not have these overexpressed receptors, and then also more than this effect on the healthy cells, MRC5. So we also tested recently these materials for pH responsive release of metal therapeutics, and then we attached two different ligands on the surface of the MSNs, and then you can see these two ligands actually here upper, and then through hydrogen bond, and then hydrogen linkage is being cleaved at weakly acid conditions, and then we release these two metal therapeutics. Both have the similar kinetics. You can see higher release at pH 5 than pH 6 than pH 7.4, and we tested the toxicity on cancer cell line, and we showed that it has higher toxicity. But we did this after pre-treatment. So we first pre-treated these materials in two buffers, 7.2 and pH 5 for 4 hours, then use this to make to transfer it to media and then to treat the cells. So even 4 hours was enough to have some effect on the cancer cells. And this is like mimicking what nanoparticles can experience in tumor tissues, because tumor tissues have extracellular matrix weakly acidic. So these nanoparticles would be experience these conditions before entering the cells. So we also worked with magnetic core shell nanoparticles, so you can see some nice magnetic nanoparticles there. And then in this, I call them cell type magnetic MSNs, because they look like cells, because super paramagnetic, you see in each particle there is one spion, and then they look like nuclei within these cells. But there can be different structures to these materials, and typically they are still super magnetic after embedding in MSNs. And also in this case, we showcase that different types of drugs can be released differently if we use different functional groups inside of the mesopore. So in case of phenyl functional groups present in the material, loading and release of this camptothecin drug was enhanced. So you can see on these CHO cells, Chinese hamster ovarian cells. And but in case without the functional groups, more effect of release of 9-aminoacridins noticed. So this is in a nice way actually that can be fine-tuned for different drugs, and then to achieve, even with this presence of functional groups, to achieve targeted delivery of drugs. In this case, we showed that using these magnetic nanoparticles and also UV responsive release of the cargo. So we use cadmium sulfide nanoparticles attached with this group, and then use it to cap the pores. And then this was showcasing combination anti-cancer treatment with cadmium. Of course, cadmium is toxic to the cells, cadmium sulfide, and then also releasing drug, camptothecin, from the pores. And you can see here magnetic nanoparticles inside, and this weakly on the surface, you can see cadmium sulfide on the external to the pores. And then you can see both, even without irradiation, there was effect on cells. But even with loaded chemical testing, but after irradiation, there was higher effect. So there is synergistic effect of the loaded drug and the capping moiety in these cases. And different types of materials can be obtained. We obtained here, and there's like a large pore, like have 2.3 centimeter cubic per gram volume, and then which can store probably large biomolecules and have higher concentration of iron oxide inside, so you can see. And regarding PMOs, so you see that organosilicon nanoparticles have these bridging molecules, organic molecules. So this is example of just phenyl, right, benzene group as R in this case. So there are some uniform nice nanoparticles obtained, but we can also use them for like to making magnetic nanoparticles, to make a coarse shell structure inside. So you can see these are more microporous now, but still high surface area. And we demonstrated that using, as I said, like core that has more active role for cancer treatment, like nanodiamond in this case. So it was embedded in different types of PMOs with ethylene and ethane groups. And then we monitored that. We showed that after exposure to near infrared light, to femtosecond laser actually, so it was capable for nanodiamond to induce photodynamic therapy, to make singlet oxygen and to kill cancer cells with this, but also we use this pore structure to deliver doxorubicin. So, and then we saw that the highest toxicity was shown in case of exposure to laser and then in presence of doxorubicin. And I can showcase also that we use these PMOs for other stuff as well. We have research related to blocking UV light, shielding from UV light, and this was early publication in 2018. But we now have that we show actually that these PMOs can be used for this. And after the difference is that after exposure to sun-simulated lamp, there was no change actually in absorption profiles. There is no degradation of these nanoparticles, which is really good, because in other cases when we use when they use actually organic molecules, there was decrease. You can see in absorbance and shielding ability, but also producing ROS when this happens. So this example, avobenzene absorbs light and then produces ROS and destroys and the environment and the cells around it. So we saw the ability, capability here, and then we now have the nice results which are waiting. Now we published for the patent to be published. We submitted the patent, and then we hopefully will publish these results soon in the paper. Also, we worked with polyurethane and nanoparticle composites, where we used the different functionalized MSNs within polyurethane structure. So polyurethane was covalently attached to the MSNs. Actually, MSNs were embedded, but the framework was covalent of the polyurethanes. But you can see that we got transparent films, as these are images of the films taken from the top, and then which were placed on the labels. So you can see that they're transparent, and we can see transparency here measuring. We also tested, we wanted to test them as coating for medical implants. So in this case, we wanted to check if they are biocompatible also, and their ability for that. And we tested how they absorb different proteins from the blood plasma, and these are most abundant, these proteins, and lower absorbance of proteins from the blood plasma means they're better. I show you that they would be less likely to induce agglomeration, blood clotting, agglomeration in blood. And so in this case, we saw that actually PEG material was, polyurethane with PEG material was the best. And also we tested how toxic they are. They are really have low toxicity, below 5%, and also high concentration of cells on the materials were noticed, and the highest was actually also on the PEG containing material, which identifies the material as a good candidate for the future applications. I would like also to say about our project, NanoFacts, which is funded by the European Commission, which is a twinning project which we obtained funding for organizing different trainings for our staff at Bioscience Institute, students, PhD students mostly, but also senior researchers. And we're organizing different types of things like we have students going to the Vienna, Technical University of Vienna or Trinity College Dublin for several months and learning different stuff like treatment of nanoparticles with cells and in vivo treatment and confocal imaging, etc. And also in Vienna, we are learning different stuff regarding cancer sensing and devising microfluidic sensors and devising actually lab on chip and organ on chip, like more specifically tumor on chip. So we are modeling chips on tumors on chips, right? And then we are making 3D models of also of tumors. So we now have this ability and hope we will expand this research also in bioscience. So this is funding intended for associated countries like Serbia is, and then partnering with two or more institutions from EU, and then expanding the excellence on this on these two topics, which were not really developed in our institute before, but now we hope we will have higher excellence in this. And to acknowledge the help of PhD students, Minja Mladenovic, who works more on mesoporosilicon nanoparticles, Alexander Pavlovic works on PMOs, and Mirjana Munjic works more on testing on cells, nanoparticles, etc., and different collaborators from EU and in Serbia, and for funding for European Commission for NanoFacts project and Science Fund of the Republic of Serbia, which funds this research in MSN-based diagnostics of cancer, and Innovation Fund of Serbia, which funds this project related to UV shielding nanoparticles. And thank you all for the attention.
Thanks a lot, Nicola, for this great talk and a very nice presentation of your activities at Biosense. It's very, very interesting. So now this is open for question. Do any of you have?
I have a question.
Yes.
Thank you, Nicola, for your presentation and your nice results. So I have a curiosity about the first part of your presentation about the magnetic nanoparticles. Seems to be in all the cases, the magnetic nanoparticles are inside of the nanopores. So my question is better or it's easier to put the magnetic nanoparticles on the surface of the particle, or it's better have the particles inside or in the nanopores?
Yes, I think it's better to have them inside, because if they're outside, they can block the pores, and they are also they can be hydrolyzed. If it's magnetic nanoparticles, they can be hydrolyzed with weakly acidic also conditions. But they are, when they are inside, they are shielded. So they are very analogous. They have characteristics similar to MSNs if we have magnetic core shell structure, but then we can just use them as they are MSNs regular. So then functionalize them. We don't have to worry if these magnetic nanoparticles, if they're outside, they can block the pores or do whatever. So some different stuff.
Okay, and the other thing, that the size of the particles are, what is the size of the particles, the silica particles?
They can be different, like typically 100 to 200 nanometers, yes.
Okay.
Yeah.
Yeah, thank you very much for your presentation.
Thank you.
Welcome.
Thank you, Luis. Any other question for Nicola? I have a quick one, Nicola. On the last part of your talk, for the sensors you developed with the polyurethane, you said that you have PEG.
Yes.
Yes. So that means that it's is it an implant, or how do you administrate the implant? Or
these were just you see like films, polymer films, embedding these MSNs. So you cannot see them here. They are very well distributed. So MSNs with PEG functionalized on the MSNs are distributed within these films. And then we hope, like, we did not test them on the implants, but we could attach them to the implants and then, transfer these to the clinics, these implants. But in this case, just we used films and then testing attachment of cells, and if their cells are healthy or that, and we will see later on this. Yeah.
Okay, that's it's very interesting. Yes, thank you, Nicola.
Okay.
We have a bit of time for other questions, if there are any. Okay, so if there is no more question, we can thank Nicola again for this great presentation and overview of activities in Serbia. It's always very nice, Nicola, to hear what you're doing and get in touch. And so now I'm very happy to introduce the second speaker of this morning session for the Netpore webinar. The next speaker is Jarno Salonen, who is a professor of pharmaceutical physics at the University of Turku, working on porous silicon for biomedical application. Jarno, whenever you're ready.
Thank you, Freddie. And good afternoon, everyone. It's afternoon in Finland already. Yeah, my topic is controlling the chemical stability and functionalization of porous silicon, but actually what I'm going to talk about is about my research history and thermal carbonization. In the first webinar, Luca told us about his history with porous silicon, and I would like to do the same, just to encourage, if there is any young student, doctoral student or postdoc listening to this, I would like to encourage them to change their research direction if they think so, and things like that, because I did that many times in my career. I made my master thesis about the quenching and recovery of luminescence in porous silicon 1994, quite a while ago. And everybody was studying photoluminescence at that time. So there was a lot of competition. So when I got a graduate school position, I changed my topic to oxidation of porous silicon, because the stability of porous silicon was a big problem at those times. Luminescence was quenching, and samples were continuously oxidized, and it changed the resistivity, optical properties, all the properties. So what I did, I studied this oxidation for 4 years, and I made my PhD thesis about it. But after that, I moved to gas sensor research. I was invited in one project where they are developing gas sensors based on porous silicon, and there was a huge problem with that chemical stability. So actually, to overcome that problem, I started to develop this thermal carbonization. I will carbonization. This thermal carbonization, and I did that for at least 4 years. And as you can see, this is the publication, my publication. During that time, where is the laser pointer? Here. During that time, I published quite few papers. I focused on the development of the treatment, and that wasn't so easy. So it took several years to do that. But it was worth it. Then from gas sensors, we moved on drug delivery studies in 2004. And I never planned to use a thermal carbonization in drug delivery applications. It was meant to be stabilization method for gas sensors and things like that. But the first ever drug loading test, what we did was with thermally oxidized porous silicon and antipyrine. And it failed really badly. After a few hours loading, the solution was boiling and bubbling, and half of the microparticles were dissolved in the solution. But actually, the reason is pretty clear. And Matei already 2000 published paper about how the pyridine vapor accelerate the oxidation of porous silicon. And if we look the pyridine, it's this kind of benzene ring, which has a nitrogen, and antipyrine has a similar structure. These kind of benzene rings, if there is some nitrogen, are always very bad for porous silicon. So, but thank God we didn't give up at that stage. Instead, we move on the thermally carbonized microparticles, and they were so stable we managed to load even antipyrine inside these particles. And after that, in that period, when we used the microparticles in drug delivery application, I managed to increase the number of publications quite a lot. Even still, our first paper released about the drug delivery using microparticles is the most cited paper. Now it has a 602 citation. So even though I developed this thermal carbonization for the gas sensor application, it was excellent considering the drug delivery application also. 2008 till 2010, we developed pulse-etched nanoparticle production with wet milling, which is much more efficient compared to ultrasound separation of nanoparticles, and the number of publication increased again. Okay, I need to be honest, this is also a lot because Helder Santos got the ERC funding, so he had a lot of researchers using our nanoparticles in drug delivery application. Anyway, the summary of this, my history, is that don't give up. So I spent 4 years to develop this thermal carbonization and published only a few papers during that period. But because of that, I have now over 270 published articles, and my H index is 74. And that's mainly because of thermal carbonization process I developed. We have used that in majority of our articles. And as I said, I changed the research direction several times. First photoluminescence, then oxidation, then thermocarbonization gas sensors, and then finally, after 10-year studies, I moved to a drug delivery application. Okay, then something about thermocarbonization. Instead of double bonded organic liquid like dicene, dosicine, andesolenic acid, etc., use it in hydrocellulation, which was developed at the end of 90s. We use small gas molecule acetylene, which penetrates quite fast, even in small and long pores. And due to the triple bond, acetylene absorbs very strongly on the silicon surface. So strongly, it may dissociate and react with silicon hydrogen bonds even before it desorbs on the surface when heated. These thermal acetylene treatment were used in early 90s. They tried to make a epitaxial layer of silicon carbide on the silicon wafer using this acetylene method, but it didn't work that well. It created a polycrystalline structure and partly even amorphous structure on the surface, but I thought that it doesn't matter in the case of porous silicon because there is no flat surface anywhere in porous silicon, so it doesn't matter if it's polycrystalline or is it amorphous or whatever, because it's chemically stable. Silicon carbide is chemically very stable. Okay. There is two different temperature range in this carbonization. If the temperature is below 600 degrees, acetylene is not reacting with itself, and the treatment can be done using continuous acetylene nitrogen flush. And it creates this kind of hydrocarbon termination on the surface, and that's why we call it thermal hydrocarbonization. Anyway, the surface needs to be fresh hydrogen terminated, and it needs to be oxygen-free atmosphere. Otherwise, this doesn't work. And that's why we quite often, if we have a little bit older samples, we dip them in hydrofluoric acid to refresh the hydrogen termination. By the way, one tip here. If you want to keep your samples fresh, put them in an exchanger with benzene there, because the hexane, because hexane vapor will fill all the pores and they will not be oxidized, so they keep fresh a longer time. Okay, and actually this hydrocarbonization process is pretty interesting. It's like a self-saturating. So you can see the weight increase when you increase the temperature, but from 450 till close to 600 degrees, the weight increase saturates. But when you go above 600 degrees, there starts to be a production of a pyrolytic carbon on the surface, and it's just fill the pores. And in FTI spectra, you can see how the silicon hydrogen bonds disappears, and you get the carbon hydrogen bonds vibration increasing here. What is interesting in thermally hydrocarbonized porous silicon, that even though it's quite stable, you can still functionalize it with alkenes and alkenes, and even with some other molecules. For example, undecylenic acid is what we use a lot. Is attached to surface quite easily, even at low temperature, around 120 degrees. And this is carboxylic acid group is very good considering the future functionalization, because you can easily activate that and link the amine into it. And we have some other click chemistry systems and things like that. There is quite a lot of these different routes to functionalize this thermal hydrocarbonized surface further. Okay, but if we go temperature above 600 degrees, we cannot use continuous acetylene and nitrogen flush. Instead, we need to stop this flush just before we start to heat the sample. And the temperature need to be raised quite fast to avoid desorption of acetylene. But this still works. The acetylene absorbs on the surface so strongly that some of them stay on the surface even above 800 degrees, which is actually what we use. We use this 800 to 850 degrees usually. It creates a pretty good surface. Still, it doesn't reduce the specific surface area too much. And what we actually, what we are creating, it creates some kind of non-stoichiometric, not actually it's like amorphous, non-arrowhead structure on the surface, which oxidized when we take it out of the treatment tube. But the good thing is that this oxide termination is very stable, and the oxidation cannot penetrate through the silicon carbide layer. So it's very stable, but still we can functionalize it further using similar silanization process what is used with silica particles, because there is great difference, interesting difference between silicon carbide and silicon surface. If you immerse silicon surface in the HF, you get the hydrogen termination on the surface. But if you dip silicon carbide in HF, you actually create OH termination on the surface. And if you have a OH termination, then you can use a silane process and attach, for example, Aptis molecules on the surface. Unfortunately, this is not that stable than those routes where we use a hydrocarbonized silicon, because this silicon oxygen silicon bond is still quite keen for hydrolysis. But anyway, it's the silicon carbide layer make it more stable compared to if we use a thermally oxidized surface. Okay. Why you need a stable surface? Okay, one reason is, of course, that it cannot react with the truck you are loading inside the pore. It should not react in different processes you are doing for the nanoparticles. This is one example. I just pick up how these particles are functionalized. So there is several steps. Start with the carboxylic acid terminated particle. We add through EDC NHS process, we add one specific molecule there. Then we do different processes, for example, in chloroform to attach something more in there. So during each of these steps, your particle, your surface need to be stable. Still, finally, in vivo, it should dissolve after a certain time. So it cannot be too stable, but it needs to be stable enough. And that is one problem we had with microparticles. Some of them were too stable. So now we have solved the problem so that for nanoparticles, we do thermal carbonization when the porous silicon is freestanding film. Then we mill it. So during the milling, we create a small amount of new oxidized areas in our nanoparticles, which initiate dissolution. And so most of the surface is very stable still, but these small new surface areas initiate the dissolution and the particles won't stay months in the body. Okay, what else? Here is what happens. Resistance, if you carbonize your sample, the resistance drops a lot during the carbonization process. So, and actually it behaves as a thermistor. And there is some other benefits of the thermal carbonization, and still we have studied that a lot. We have developed several functional routes, and we have used that in many different applications. But still, we don't know exact structure of this thermally hydrocarbonized layer. It's impossible to figure out. There is a hydrocarbon species, there is some double bond still left from the acetylene molecules and things like that. And more importantly, we don't understand why it reacts with alkenes and alkynes similar way than thermal hydrocellulation. We don't know why it happens, but it works, so we don't mind. Then, by the way, one hint for new researchers that porous silicon is very interesting material. After you have produced it, and you have a certain pore size distribution, you can change it afterwards using thermal annealing. You can increase the pore size quite a lot. So you don't need to try to increase the current density and things like that. You can make the pore size distribution, which is fine for you, and then afterwards change the distribution, enlarge the pores. Thank you. I think that was, I don't have any more tips for the young researchers.
Thank you very much, Jarno, for this great, it's a great presentation, and I think it's a very interesting format also to tell the story, which is your story about how to stabilize porous silicon for the different application that we are working on. It's very interesting to give these tips to the youngest scientists as well. It's a long way getting to these very nice results. And it seems that you have a very, very nice control of what you
and sometimes during your research career, you just need luck, like this drug delivery thing.
Yeah,
we developed thermal carbonization for gas sensors. Then we start to try drug delivery, and right after the first test, we figure out that, okay, now we need this thermal carbonization even in this application.
Yeah, it's a very nice process. It's pretty famous in the community for a simple reason. I think is there are not many ways to stabilize porous silicon, which is good somehow. It's what you just said. It's important to have them do their job and then be stable, but then it's what we want them to be eliminated at some point, especially in vivo. And that's the threshold. I will open the discussion now for question, then we can talk again if we have time. Is there any question here for Jarno? No, I'm watching if anyone is raising hand.
I have a question for Jarno.
Yes.
Happy to see you again, Jarno. And well, thank you for your very interesting presentation. Well, you get a lot of amazing results. So I have a question about this layer, this thin layer about silicon carbon layer you get during your stabilization. And I wonder if it's possible to control the thickness of this layer. I suppose it's a very thin layer, and if you can control very well the thickness. And the other thing is about the temperature. So you can improve the stability when you increase the temperature, no? So I suppose the morphology or the chemical or probably it will be more crystalline when you increase the temperature. It will be more stable than the surface and the material when increased more than 600 Celsius. I don't know, 800 or more. So this is a way to improve, or there is a temperature, optimum temperature for the stability?
Yes, it's the over 800 degrees. When you treat it over 800 degrees, it creates this hydrogen-free silicon carbide layer. It's much more stable compared to hydrocarbonized.
Mm-hmm.
But what I forgot to say, that the hydrocarbonized surface is actually hydrophobic. So in aqueous solution, it make it, I would say, more stable, but silicon carbide layer, which is terminated by oxygen, is hydrophilic. And that's why we have to use that in, for example, in our humidity sensors and in gas sensor applications. The control the thickness of the layer is more difficult. I think you can control it a little bit with temperature, but I'm not sure how much. The treatment works quite well also around 700 degrees of Celsius, what we have used for optical reflector structures.
Yeah.
Optical reflector structure cannot stand 850 degrees, so we need to use a little bit lower temperatures. But if you go above 900 degrees, I think it doesn't give much more thickness, increase the thickness. What we have used different methods to determine the thickness, and it's usually, if it's 800 to 900, the thickness is 1.5 to 2 nanometers, which is actually quite a lot in porous silicon, because the length of matter is actually quite small. But the control of that is a good question. We have never tried to control that. There is so many parameters. You could spend 10 years to studying simply the effect of different parameters.
Well, that's good, Jarno. You have more work for the future.
I'm trying to apply that now.
Yeah, I suppose that.
Yeah.
Anyway, thank you very much for your very amazing presentation.
Yeah, good luck for Saeed.
Yeah.
Trying to apply that now.
Bye.
Are there any questions for Jarno?
Well, good morning, Yana. How are you?
Hi, Jeff.
Nice to see you. What time is it in Texas?
Oh, it's not quite 5 o'clock.
Yeah.
5 o'clock.
Thanks a lot for.
But see, if Yarno won't come to us, I have to come to Yarno.
Thanks for attending the webinar.
So Yarno, I do have a quick question. So if there's things about the layer, how would you distinguish, say, for example, the density of the thermally carbonized layer relative to, say, silicon carbide itself? Is it relatively amorphous, disordered, lower density? How would you describe it based on what you know?
The density must be. I think I don't actually know. It might. I assume the density is lower, but actually it could be also. It depends on the bond length. If you have a amorphous, use it. I doubt it's like water. So because it's non-stoichiometric, it must be smaller compared to silicon carbide, I think.
So there's a research problem for future students right there.
There is a lot.
There's a lot to figure out. Yeah.
There is so many. It's quite difficult to study these that thin layers, how it affect. We tried to make a optical simulation using 3-parameter effective medium approximation, and it worked somehow, but still it's very difficult to study more precisely. We have tried to use all kind of instruments we can get, and still it's partly mysterious. We are like engineers. If it works,
Did you ever use XFs? Ever use XFs?
Yeah.
Yeah.
Yeah, we have used, and all kind of methods. One problem is that silicon carbon bond is actually quite annoying in many sense. For example, if you try to if you have this kind of a silicon carbide layer, there is no single peak in FKI spectrum. You have this broad what is Beerström broad band there. There is no nice peak telling you that here is the silicon carbide one. And it's a little bit similar situation in XPS. The silicon carbide peaks are mixed with oxide peaks, and it's quite difficult to distinguish these two. But yeah, we have used all kind of instruments from the, even SIMS and actually SIMS was pretty good because we try to look how uniform carbon content we have as a cross section. So how thick films we manage to carbonize, and we found out that even up to 70 micron, we had a quite stable. In the middle of the pores, we have only 50% of that amount of carbon compared to the surface, but I think it's still pretty good considering the thickness of the freestanding film.
Very good. Nice work on it. Very good.
Yeah. Thank you. Thank you, Jarno. Other questions? We are running on time, by the way. Thank you very much. Thanks a lot, Jarno. Thanks a lot, Nico, for your great presentation. It's good to exchange. I hope it will be very helpful to the others and the other participants, and that we can continue to interact by email, of course. And if any of you needs to get in touch with the speakers directly, let us know. Luis and myself will be happy to put all all the participants in contact if necessary. Thanks again to everyone, and see you in a month. Thank you very much.
Thank you.
Thank you, Freddy, Jarno, and Nicola.
I'm still looking for the opportunity to see you guys.
Yeah, it's been a long time.
It's
Happy to see you.
been a long time. Yeah. Thank you.
Thank you, Jarno. Thank you,
Thank you,
Nico.
Nicola and
Bye,
Jarno.
Luis. Bye,
Thank you
Jen.
all. Bye bye.
Freddy, see
Bye,
you.
everyone.
Bye.